All right, welcome everyone. Waiting for everybody else to join in. How was the assignment? The last assignment you have taken on interference?
So it was fine, sir.
You did not find it very difficult, right? It was manageable.
Yes, sir, manageable. Like obviously, like all assignments have few hard, few like simple types, so it's fine, sir.
Hmm. I heard that your schools are starting from 1st of June now. Is it correct?
I don't know, sir. We haven't received any notification to you.
Which school?
HSR so far 21st only.
NPS HSR.
Yes, sir.
Okay.
So I think Indranagar is also on 21st.
Indanagar is also 21st.
So they've not sent out a confirmation email, but they've kind of hinted at a 21st starting.
Okay. I think, I don't know, I have heard it from Kormangla. Probably it is valid only for Kormangla kids and for some specific classes only, not for entire school. But anyways, let us see whatever it is. So maybe for you know couple of months, your school will also have online classes. So in the morning, you'll be attending the school classes, and in the evening, alternate days, you'll be attending the centum classes as well. Okay, so manage your time accordingly, and yes. All right. So today we will continue from where we have left off, the wave optics study that we'll be doing. Earlier, the plan was to finish off wave optics quickly in half the session, and then other half, I was thinking of doing, other chapter, current electricity. But yesterday, with NPS Rajajinagar, we have spent entire 4 hours on wave optics only, solving different kinds of problems and finishing up the chapter. So same thing we'll be doing here as well. So we'll not rush forward to a new chapter. Instead, we will look at different type of question also whenever we get time. All right, so let us move on. Like what we have discussed earlier, that the most important thing in this chapter. Okay, just give me a moment. Sharing of screen sometimes create trouble.
So wait, this week there was only one assignment, right?
What do you mean?
Like on Learnist, there was only one assignment, the YDSC one, right? That's all.
Yeah, that is what we had done.
Yeah. Okay.
Okay. And yeah, I mean, you have other sources also to solve problems. So if you think that you have time, please move ahead and do every sort of question. Okay.
Yes, sir.
And and those who are preparing for JEE advance, you have to go beyond everything, like so open-ended that you may learn theory also by solving questions. So it is never-ending process. So don't constrain yourself by just the assignments that are given to you. All right. So what I was saying was the most important thing that we had discussed uh, was Young's double slit experiment. Okay. So we will spend a little bit more time on Young's double slit experiment and the interference, solving a few more questions on it before proceeding with the further concepts of the chapter. Okay. So one thing that I wanted to discuss with you is another way of finding the the path difference in a Young's double slit experiment. Fine. So all of you please write down YDSC again. YDSE. So in the previous session, we have we have used Pythagoras theorem to sort of come up with the expression of the path difference. Now we will use trigonometry, and it will come out to be very easily. Why we are using trigonometry? Because many times you will see in the questions itself they'll be talking about the angles that we'll be dealing with here. Okay, so all of you draw the Young's double slit experiment, then it'll be clearer what I am saying here. Two slits like this, and then there is an axis. Fine. So wave from here and there, these two waves meet there. Okay, this is, let's say, wave 1, and that is your wave 2. These two waves meet at that location, which is at a distance of y. Okay, this distance is y. So we have found out the expression for the path difference in terms of y, small d, and the capital D. Can anyone tell me what is the path difference in terms of these three? How much it was? At this point, what is the path difference between wave 1 and wave 2?
And lambda capital D by D.
Path
Y
difference.
small d by capital D.
Oh, sorry.
Y into small d by capital D.
Yeah.
So path difference is y small d by capital D. This is what we have derived. Okay, when this path difference is n times lambda, constructive interference. When this is equal to 2n plus 1 lambda by 2, it is destructive interference. Fine. So it is all about path difference and phase difference. So now same expression we can arrive at by using some sort of basic trigonometry. Fine. So if I join this center line over there, this is an hypothetical line. This doesn't exist actually. It's just a construction. Fine. So what was what were the set of assumptions that we have made whenever we talk about Young's double slit experiment? The assumptions are that capital D is very large compared to small d, and y is very less compared to capital D. Fine. So based on these two assumptions, what can be said? Anyone? Said about wave 1 and wave 2. Wave 1 and wave 2 are approximately what? What I can say? They are parallel. They are parallel. As if they are meeting at infinity. Far away point they are meeting. And and then this angle, which is made by this also and this also, because all three lines are parallel, so we can assume that these angles are same because they are all parallel. Fine. And since the small y is also very less, I can say that the angle made by this line, which is made by that line also, this angle theta is very small. Fine. Theta tends to 0 because y is very small. So these are the outcome of how you, I mean, whatever assumptions we have made on Young's double slit experiment. Fine. Now, if you have two parallel lines, how do you find the distance, or sorry, the difference in the lengths between the two parallel lines? How do you find that? You know that wherever they end, that is the same point. Okay. So if I consider that they are ending at same point, their endpoints are same. So here they're ending. So what is the, how do you find the length difference between these two? Anyone? What is the construction you have to do?
So you drop a perpendicular from. Oh wait, no.
Correct. You have to drop a perpendicular and then measure this distance. Fine. This is the answer. This distance is the path difference between these two. Fine. Same thing over here also you can do. Fine. So you can drop a perpendicular like this. Suppose this is a perpendicular. Fine. So this is the path difference. This one is the path difference between the two waves. Fine. So now can you tell me how much is this path difference in terms of small d and theta? Before that, can you tell me what is this angle? This angle is what?
-90 minus theta.
Is that a guess?
No, sir, that's not so.
Anyone else? How much is this angle? Basic trigonometry or geometry? No one? Acha, tell me how much is that angle? This one.
So it's a theta.
This angle is how much?
That's 90 degrees.
That's 90.
It's 90 minus.
Which answer that?
It is 90 minus theta. And this is 90. So this has to be theta. Okay. So delta x is what? Now tell me in terms of d and theta, what is delta x?
D sine theta.
D
D sine theta. Okay. And since theta is very small, I can say this is roughly equal to d tan theta. Fine. And the angle tan theta can be written as, tan of angle theta can be written as y by d. Okay. So this way you can find out the path difference without using the Pythagoras theorem easily. Fine. And this is the more preferred way of finding the path difference in every other book other than the NCRT which you are following. So, please start using this. This is the best way to find the path difference. If you are assuming two waves are parallel, just drop a perpendicular from starting point of the first on the second one. So this should be the path difference. Okay. And using trigonometry, you can say delta x is d sine theta, which is d tan theta, and tan theta is y by capital D. Okay, so like this, you can, anytime, whenever you forget the expression for the path difference, you can quickly do this and you'll be able to recollect from your memory. All right, so there is another experiment of the interference that we haven't discussed earlier, and that was interference from films. Write down. Interference from thin films. It is not exactly a part of your NCRT curriculum. In fact, this you can say it is like a numerical only, which I am showcasing as if it is a part of theory. Fine. So it's like a numerical that is asked regularly in the competitive exams. So I thought of discussing this with you guys. Okay. So before I even discuss this, have you guys ever, experienced this thing that suppose oil is spilled on the surface of the water and you're walking past through it and you're able to see different colors on the film as you're walking past through it, and sometimes you see complete brightness, sometimes you see some dark patches on it, sometimes you see red color, then blue color, and things like that. Have you ever experienced that?
Yes.
Right? So if light behaves like a ray, this should never happen. Okay, what is happening is interference is happening. Fine. So for example, if the red color is undergoing constructive interference at and violet is getting destructive interference, you will see red color prominently. If blue color undergoes constructive interference, depending on your angle of viewing it, then you will see prominent color as blue. Fine. If everything having destructive interference, you'll see a dark patch over there. Everything constructive, you'll see a bright, patch over there. So this is what is happening, and let's see mathematically how we can analyze the situation. Okay. So consider a thin film. Suppose this is a thin film. Fine. And and let's say thin film has a thickness of T. Fine. This thickness is T. All right. Now, light comes and hits the film of, this is, by the way, oil of refractive index mu. This is air, and this is also air. Okay, just for the sake of simplicity, I've taken both sides as air. So this is the normal. What will happen?
Refraction.
Only refraction. Reflection won't happen.
So both like.
Part of it will get reflected, part of it get refracted. Fine. This is the reality. This is what happens. Fine. So whenever we study reflection, we ignore refraction and vice versa. But this is what happens. So light will just, is this the complete picture or something else will happen?
Here also.
Here also part of it will be reflected like this. Okay. And let me draw the normals. See the normal over here. This is a normal over there. So now light will come out. When it come out, it will be parallel to the reflected one. Okay, and it will not stop here. It will keep on doing this. Fine. Part of it will come out. Part of it will come out from here. So this will keep on happening. Fine. But the intensity of these lights, these ones, are very, very less. Fine. So if you're considering the interference, if you consider only these two, wave, let's say this is wave 2, this is wave 1, and this is wave 3. If you consider only wave 2 and wave 3, it is sufficient to understand what will happen when these two waves constructively or destructively interfere. You don't need to worry about the infinite waves that are coming out of multiple reflection, because the intensity of after one or two reflection becomes extremely less. You can ignore them. Fine. So consider just wave 2 and wave 3, let us say. Fine. So between wave 2 and wave 3, between wave 2 and wave 3, we need to find the path difference, because we are talking about the interference here, and the center line is path difference. So if we find path difference between wave 2 and wave 3, we'll be able to understand what will happen because of the interference. Fine. The assumption here is, every time we are dealing with assumption in optics, the assumption here is that number one assumption we have already discussed. The other After one or two reflection, the intensity goes to 0. Second assumption is angles are very small. Okay, angles are very small, or you can say the observer is near to the normal. Near to normal. Okay. Now tell me, what is the path difference between wave 2 and wave 3? Try it, all of you. Net path difference, how much? Anyone?
So can we approximate the distance that it covers inside that thing to just be t? So then the total will be 2t.
Yeah, of course. Why not?
So then is the path difference lambda by 2 minus 2t?
Why lambda is coming up in path? No, it doesn't matter what is the lambda. Path is path. How it is depending on wavelength?
Because W2, it has a hard reflection. So it has to get a path difference of lambda by 2.
Okay. Others? What is the net path difference? Only lambda by 2 you are saying.
So it's lambda by 2 minus 2t.
Okay, that is wrong. See, second, this one, wave 3 is traveling a distance of 2t in a refractive index of mu.
Oh, yes, mu into 2t.
So 2 mu t is the path difference because wave 3 is traveling an extra distance. Okay, and you can see there is a there is a hard reflection. Let's say this is 0.1 and that is 0.2. Okay, so at 0.1, the reflection is from the hard reflection is from higher refractive index, higher mu. Okay, so this is the hard reflection. At point number 2, reflection is from rarer medium. You can see here the reflection is from air to mu. Over here, the reflection is from mu to air. Okay, so 0.1 is hard reflection, 0.2 is soft reflection. So this is soft reflection. So wave 2 is undergoing one hard reflection, because of which lambda by 2 path difference will come in, and the second point, there is no hard reflection. So only lambda by 2 extra will come in. So total path difference, you can say, will be equal to 2 mu t plus lambda by 2 or minus lambda by 2? Plus or minus?
It won't make a difference.
The same thing, sir.
Doesn't make a difference. Fine. So this is the path difference. Fine. Now when this is equal to n times lambda, what will happen?
There'll be
Constructive.
It will be constructive interference. Constructive. So for those wavelength for which this equation is satisfies, then for those wavelength, constructive interference will happen. Or you can say that 2 mu t, when this is equal to 2n plus 1, lambda by 2n plus or minus 1, doesn't matter, depending on value of n. Fine. So this is for the constructive interference. Now for the destructive interference, 2 mu t plus minus lambda by 2, this should be equal to 2n plus 1 lambda by 2. Okay. So you will get 2 mu t is equal to what? You'll get n lambda then plus lambda by 2 plus minus lambda by 2. So it doesn't matter. If it is minus, then lambda by 2 is gone. If it is plus, it becomes plus lambda. So it is n plus 1 lambda. N plus 1 lambda is n lambda only. N is an integer. Okay. So you can keep it like this. So if this happens, then there will be destructive interference. Okay. Now don't treat it like a formula. I'm cautioning you, do not take it like a formula. You start mugging up the formula and then trying to substitute it in the numerical, because this is valid only in this particular case, only in this case. What if there is a water here down, there is water whose refractive index is more than the oil, then even 0.2 is hard reflection. Okay, then this thing will reverse. This will be for constructive and that will for, sorry, this will be for destructive and that will be for constructive. Fine. So I'm just taking this example to elaborate how you should deal with the interference from the thin film. Okay, and there can be multiple scenarios here. Any doubts? Any doubts on it?
So which distance do we assume is 2t?
See, wave 3 is traveling this distance and that distance, right? So this distance is roughly t, and that is also t. But they are these two distances are inside a refractive index of mu. So total optical distance you have to take 2 mu t.
Yes, sir.
Any other doubt?
So what is a thin film exactly?
It can be anything. It can be film of oil. It could be little small glass slab that is kept. Could be anything.
Okay, sir.
All right. So now let us discuss few numericals based on the interference, and then we'll proceed forward with another part of the chapter. Okay. Fine. So let me find out. This one.
So is the answer C?
Don't speak up the answers. Others are also doing it, right? You can type it. When I'm asking you to speak, then you speak.
Yes, sir.
Param, it depends on, this is an approximation. When you're still, you're reviewing it from normal, then this will happen. But if you move, this approximation that we have taken will not be valid. Angles won't be small. All right, so I can see many of you have already answered. Okay. Fine. So the correct answer is C. Okay. How it comes? The intensity formula for, is I1 plus I2 plus 2I1 I2 cos of phi, right? So the maximum possible intensity is root over I1 plus root over I2 the whole square Okay, and minimum possible intensity is root over I1 minus root over I2 the whole square. Fine. So this will be equal to 9 I square, you can say, and this will become I square. So answer is this. Sorry, not I square, only I. So do not start adding and subtracting the intensity. All right. Intensity won't add and subtract. Intensity will follow I1 plus I2 plus 2 I1 I2 cos phi that we have derived. Fine. Um, this one I think you can do it quickly.
So oh no. So I think we did something really similar last time.
Yeah. So should be getting the correct answer then. Done?
1 second, sir.
Okay, Vikas got it.
Yes, sir, got it.
Type out. Okay, so different answers I'm getting. Some calculation error you guys are doing somewhere. Fine. So here it is how you should do it. First of all, it uh, anyways. So first of all, you should know the formula for the maximum, right? Maximum for the first wavelength is N1 lambda 1 d by small d. This is Y1 for lambda 1, and maxima for the second wavelength, the distance is N2 lambda 2 d by small d. When the maximas coincide, then N1 lambda 1 d divided by small d should be equal to N2 lambda by 2 d by small d. Fine. So from here, we'll get lambda 1 by lambda 2 is equal to N2 by N1. Fine. So this is 5 divided by 7. And 5 and 7 are the least values in terms of integer to satisfy this equation. So N2 should be 5 and N1 should be 7. So you can use this, put N1 as 5 and lambda 1 as 500 nanometer, and d by d is given as 10 to the power 3. Don't make silly errors in calculation. Okay, we are not learning how to calculate here. Just make sure you don't make silly errors there. I hope the questions were clear. Move to the next one. This one.
So what's the answer for the last one?
You can calculate now. It's just direct substitution. Focus here.
Okay, sir.
If I remember correctly, it was 3.5 into 10 to minus 4. But I'm not here to tell you how to multiply and divide. Okay, Ruchir Singh got it. Others? Vikas, Akshit, Hia. Ruchir Parekh is getting different answer. Okay, people are getting different answers. Fine, so let us have a poll. Take the poll. Mehul, capital D is not required. Previous question, capital D by small d is directly given. You don't need to know what is capital D and small d. Capital D by small d is given to you directly. All right, so this is what people are saying. Option B and yes, option B is correct. And the only reason why you may get this question wrong is by making calculation errors. Fine. So let us see how to go about this. 12 fringes are observed to be formed in a certain segment of screen of wavelength this. So 12 should be equal to what? 12 should be equal to length of the segment divided by the the fringe width in the first case. Okay. So this is your first equation. You need to find out how many fringes now in the same length. So n divided by 12 is equal to beta 1 by beta 2. Beta is proportional to lambda. Lambda d by d is beta. So this will be equal to lambda 1 by lambda 2. So n is equal to lambda 1 by lambda 2 times 12. So you'll get this as 18. Okay. Clear, right? No doubts. This one. Do the first part. Second part is similar. Okay. Many of you got the answer already. Others? it makes sense to draw the Young's double slit setup, a small one. It'll help you to visualize. Okay, all of you listen here. Part A we are doing. Okay, intensity should be half the maximum. The formula for intensity is 4 I naught cos square phi by 2. Half the maximum means maximum is 4 I naught. So half of it is 2 I naught. So intensity should be 2 I naught. So for that, you'll get cos square phi by 2. This should be equal to 1 by 2, right? So cos of phi by 2 is equal to 1 by root 2. So phi by 2 is how much?
45.
No, that's only one.
Plus minus.
It'll be n pi plus pi by 4. Not just plus, you can say plus minus. Okay, so there are multiple values of phi for which cos of phi by 2 is 1 by root 2. Do you think that there will be only one point which will have intensity half the maximum, or there will be multiple points? What do you think?
Multiple.
Multiple points. So that's why there will be multiple phi values. Okay, so the value of phi will be equal to 2n pi plus minus pi by 2. Okay, so this is the phase difference that should be there. Now here, if it would have been written that find the minimum distance, then you should have taken the minimum angle. Okay, but here it is not written that you have to find the minimum distance. So that's why it will take a generic value of phi. And the if they are asking you to find the distance, right? In terms of distance, I can write down the path difference. In terms of distance y, I can say that the path difference is y d by capital D. Okay, so if this is the path difference, phase difference is 2 pi by lambda into this. Okay, this is the phase difference corresponding to that path difference. So this should be equal to 2n pi plus minus pi by 2. Any doubts till now? Anyone? Okay, no doubts. So pi is gone. Fine. So you'll get y to be equal to, I can take 2n plus minus half over there. So y is equal to d lambda by 2d, like this. Okay, so keep putting the values of n, you will keep on getting different values of y for which intensity is half. All right, so never forget that there will be a generic value of phi that will exist. So when you learn inverse trigonometric function in mathematics, you'll understand what I'm talking about here. Okay, so huh.
So, is it right to do it using symmetry, because to save time, like distance between a dark and a bright one will be lambda d by 2d, and half has to be between that. So can we say lambda d by 4d?
You can say that, like, with practice you will get to learn these kind of tricks. Fine, and but then there is not just one value; there are multiple values.
Yes, sir.
And yes, even that you can get by analyzing a little bit more. Every time between those, you'll get it. Like between not only just these two, the next two also. So like that, if you find out the pattern, you'll directly get the answer also. Okay. But since it is half, it is lying in between. Okay. But if it is 1/4, it need not be linear correlation. Now it will not be 1/4 the distance. Are you getting it? The mean is always in between, but it doesn't require 1/4 of the maximum to be 1/4 of distance. So that method won't work in the B part. Getting it, Ruchir
Yes,
Singh?
yes, sir.
All right. So let us take one more question. We'll take two more questions. Just two more. Do this one. What is the answer? You don't have to do any mathematical this thing. You just need to find out the symmetry. You need to find locus of the points which are having the same path difference. Depending on that, you can answer it. Anush got it. Akshat, Ruchir. Okay. I hope you have read the question properly. It's a part of the cylinder. No, it will not be. Okay, anyways. Somehow I'm not able to make it three-dimensional object. Doesn't look like three-dimensional. There should be something from the base that should come like this. Now it looks like 3D. Okay, fine, whatever it is. So this is a cylinder. So you can see that all these points on this straight line, they all, when they go and hit the bottom and reflect off, they all will come together and they all will have the same phase change. So all these points, they are in phase. All these points on a straight line, they are in phase. So they will interfere and produce patterns which are straight line only. Okay. So you need to just look at the points which are in phase. So then only you can get it. There is no mathematics here. You just need to visualize it. Okay. Still, okay. Anyways, drawing is not my forte. We'll take one more question. This is the last question before we get ahead with the chapter. Anyone got the answer?
So 1 second.
Okay, Shreya got something. Okay. Fine. Listen here, all of you. So there will be one portion of light that will be reflected off. Some portion will get transmitted like this, then reflected, then it will be like this. Okay. So it is like the thin film interference, similar to that. Okay. So here intensity is I. What will be the intensity of this one? This light?
By 4.
I by 4, because 25% is getting reflected. What will be the intensity of this one? This one.
9I by 64.
Acha, tell me what is the intensity for that one? This one.
3 by
3I
4.
by 4.
3I by 4. 3I by 4 into 1 by 4 will be this. Right?
Yes.
This is reflected. So 3I by 4 into 1 by 4 is 3I by 16. Okay. Then part of it will get reflected. So 3I by 16
Into 3 by 4.
into 3 by 4. Are you getting it? All of you?
Yes, sir.
So this is 9I by 64. All right. Now I1 is I by 4 and I2 is 9I by 64. The maximum intensity is root over I1 plus root over I2 the whole square. You need to find ratio, is it? Find the ratio of the minimum and maximum. Maximum to minimum we can find out. Inverse of that is the answer. That divided by root over I1 minus root over I2 the whole square. So here you will get it as 1 by 2 plus 64
3 by 8.
3 by 8 divided by 1 by 2 minus 3 by 8 whole square. What is the answer? Anybody got that?
49, I think.
What you think? And
That's
anybody
49.
got
49.
49. Okay. So this is 49 is to 1. That is the answer. Okay. So so some integer type question can come in J advanced, something like this. And you can see it was a 7 marker, but way back. It was a 30 years back. All right, so let us continue with the chapter and discuss the new section of the chapter, which is diffraction. Okay. Can anybody tell what is diffraction? I think we had a very brief introduction of it when we started the chapter. Anybody remember diffraction? What it is?
So it's like light bends around the corners or something.
Okay. Light bends around the corner. That should not happen if light is a ray, right? But still it bends around the corner. It doesn't go straight. So, correct, bending of light around the edges of the objects. Okay. In fact, you can very well observe it from, let's say, there is an obstacle. There is an obstacle here. I think we have discussed it. There's an obstacle and there's a light source here. Light will not go straight up like this. If there's a screen here, some portion of light will come here also, as if light has bent. Okay, so if there's a diffraction happening, that diffraction doesn't happen because it's a ray phenomena, and hence if there is a diffraction shown by the light, it can be said that light is behaving like a wave, because diffraction is a wave phenomena. Something like sound also easily bend around the corner. It is not like somebody standing at the edge will not hear anything. Sound will come to the eye, to the ears of that person as well. Anyway, so diffraction is understood in your syllabus with by using an experiment. Okay, and that experiment is called single slit experiment. Please write down single slit experiment. Double slit experiment was demonstrating the uh, interference. Single slit demonstrates the diffraction. So let us see what it is. First, we will draw the experimental setup. Okay. So there is a plane of the slit, and there is this screen. Okay. You can say that only one slit is there. So we can show its opening here. And there is a center line. This one is a center line. Okay. This distance is like previous. It is D only, capital D. This is capital D. This one is A from here to here. This distance is small a. Okay, this is small a. Now, over here, we are studying, let's say, at a distance y above the center line, we are trying to see what is happening. Okay. Ideally, there should not be any light reaching at that point if light behaves like a ray. What should have happened is light goes straight here and light goes straight there if light is coming parallel. Okay, and you see a bright patch over there. But here also light reaches. The reason is light behaving like a wave. So what happens is when a source is kept over here, let's say this is a source, it will generate, let's say, spherical wave fronts like that. When it comes near the opening, according to Huygens principle, all the points on this can be treated like a new source. Fine. So in order to understand what is happening in a single slit experiment, you need to assume that there are multiple sources. I'll just draw a couple of them, but there are many sources. You can assume that all these points are behaving like a source. Fine. So if they are behaving like a source, there can be multiple waves that are coming at that point. Fine. There can be waves from here, from there, from everywhere the wave reaches that point. Okay. So we need to understand how these family of waves will undergo the, yes, Ruchir. So we need to understand how these family of waves will undergo the interference. So diffraction is nothing but interference of family of waves. Okay, that way you can understand what is going on in the single slit experiment. Fine. Now one doubt will come in our mind. In in double slit experiment also, we can consider that diffraction is happening with one slit and with the other slit also. That is very true. You can assume that. But apart from that, the wave coming from slit 1 is also interfering with the waves coming from the slit 2. So interference is dominating over diffraction over there. You'll not be able to observe it completely. Okay. And anyways, till now, none have satisfactorily explained the difference between the diffraction and interference. It is just that whenever we study diffraction, we study it like this, and whenever we study interference, we study it in a different way, the way we have studied the interference in Young's double slit experiment. Okay. Now, here also the assumptions are there. Okay, same assumptions. Write down the assumptions. Write down. First, you write down the assumptions. First assumption is the A is very less compared to capital D. Second one is Y is very less than the capital D. So whenever it is written that it is a single slit experiment, you need to, assume these things. Small a is the width of the slit opening. Okay, from here till here, that distance is small a. Okay. Now, using these two assumptions, can you tell me what is the path difference between that wave and this one? Wave 1 and wave 2. What is the path difference at that point? I can assume it that two waves are parallel.
So this.
No one? What is the path difference between wave 1 and wave 2? You can get it easily.
You do the trigonometric way.
Say it again.
So do we do it using the trigonometric thing which we did?
Anything you do, man. Tell me the answer. Okay. You can use trigonometry. That is faster. Okay, here got it. Drop a perpendicular. This distance is the path difference. Okay, so you can have a center line. You can have a center line from here. It looks exactly same. Geometrically, the situation is exactly the same. Instead of D, it is small a. That's all. Fine. So you can say that the path difference delta x is small a sine theta, which is roughly equal to small a tan theta, which is equal to small a y by d. Okay. Now, if small a y by d is equal to 2n plus 1 by 2n plus 1 into lambda by 2, can I say there is a dark fringe over there? Can I say destructive interference happens there?
Yes, sir.
Yes, sir.
Okay. Others?
No, so but like there's going to be light coming from all of the points, right? So even if these two just destroy them, like
Exactly. So that was a trick question. So even if these two waves are having destructive interference, what about the waves coming from the other points? They need not have destructive interferences. Fine. For example, if let's say another wave comes in from here, this wave goes here and another wave goes there. These two waves need not have destructive interference. Wave 1 and wave 2 will have, but these two might have constructive interference over there. So you may not be able to see a dark fringe over there. There might be some brightness. So we need to consider, write down, we need to consider entire family of waves for interference. to study diffraction pattern. Okay, now there are infinite, ways, like the way we have been studying it. It'll be extremely difficult to take two at a time and then count one by one and finish off all the ways. Fine. So there has to be some sort of trick, and this is what we are going to discuss next. All of you draw this setup again. I can just erase it and reuse it, but all of you have to redraw it. Redraw. I'm waiting for all of you. Till here you redraw. Done? Okay. So now what I'm doing is I'm taking a point at the center and a point at the top. From these 2 points, these 2 waves are coming and interfering here. What is the path difference between these 2 waves? What's the path difference?
A by 2,
by 2,
Y by D.
E by cap.
Correct. So A by 2, A by 2
A by
tan of this angle, right? All these lines are parallel only. A by 2, Y by D. This is the path difference. Okay. Now you will observe one thing, that suppose I take these 2 points like this. My upper finger is the upper point and the lower finger is a middle point. So if I move my hand like this when I'm moving, little bit when I move down, the upper finger will move little bit down, the lower also little bit down, but distance between these 2 will remain A by 2. Okay, like that, if I continuously move down and if I consider any point in time, let's say the upper finger is here and lower is here, distance between them is still A by 2 only. So if I consider these 2 points, what will the path difference between these 2 waves when they meet here? Will it be same or different?
It will be same.
It will be same. A by 2, Y by D only. Right now also A by 2, Y by D. So like this, if I keep on moving and the upper point comes to the center, then lower point goes to the here, the let's say point 1, center point is let's say point 2 and the bottom point is point 3. When point 1 reaches point 2 reaches point 3. So when I'm moving it like that, I have covered all the points, taking 2 at a time. Okay, so like this, if I consider 2 at a time, every time you'll see these 2 waves will have a path difference of this much. Okay, so if this is equal to, okay, if this is equal to 2n plus 1 lambda by 2, what I can say? Can I say dark or destructive interference, right? So I can say that y is equal to 2n plus 1 lambda d by a. Destructive interference should happen, right? So what does it mean? It means that odd multiple of lambda d by a, destructive interference should happen. Now, why don't I take 2 points which are separated by a by 4 distance? Let's say 1 and 4 over here, and then start moving it down. Even that way also I can consider, right? Why should I take a by 2 only? Isn't it? So like that also, if I move, then also I'll be able to consider all the waves. So if I move it like that, then the path difference will be a by 4 y by d. So when this is equal to 2n plus 1 lambda by 2, dark or destructive interference will happen. Or you can say y is equal to 2 times of 2n plus 1 lambda d by a. This is what? Even multiple of, right? Even multiple of lambda d by a. Okay. Now instead of a by 4, if I take a by 8, will I get anything new? Instead of 2, I'll get what?
4.
4. It will be again even multiple of lambda d by a only, right? So combining these two equations, okay, these two, if I combine these two, it means that any multiple of lambda d by a, there will be destructive interference. Fine. So y is equal to n lambda d by a, it will be destructive. Okay, and y is equal, in between destructive there will be constructive, and y is equal to 2n plus 1 lambda d by 2a will have constructive interference. Okay, these two things you should remember, and you can see that the formulas are counterintuitive because similar kind of formula for destructive was there for constructive in the Young's double slit experiment. Fine. Okay. Now tell me one thing. Where is central maxima? Where it is?
So there won't be central maxima. It'll start with the first fringe.
Okay.
So
Others? What is the definition of central maxima?
Bright fringe at center.
Centum?
So the bright fringe will be at the center. Why is
I am
equal to
asking
0?
you something else. What is the definition of the central bright fringe? Definition क्या है भाई?
So it's supposed to be the place where both of the waves have zero path difference.
It's correct. It's a point where the path differences are zero. Whenever two waves are interfering, the path difference is zero. Okay. So if you consider the center point, okay, one wave from the top and one wave from below. These two waves can consider zero path difference. These two waves, again zero path difference. Fine. So every time you take a wave at the top somewhere, you'll get another corresponding wave at the bottom with which the path difference is zero. Okay. So that is the reason why the center here has zero path difference for all the family of waves. So central bright is at the center. So this equation, when you are using for destructive interference, n doesn't start from 0, n starts from 1, 2, 3 like that. Or you can put n equal to minus 1, 2, 3 also. This one you can start from 0 because you're using plus. If you would have been using minus, you could start from 1. And negative integers also will be valid. Any doubts, anyone? No doubts? There will be a central dark instead of, right? Okay, no. All right, so now tell me the width of central maxima. All of you.
So lambda d by a.
I mean, whenever I'm asking you something, there has to be some catch. Okay, so don't immediately answer it without even writing it on your notebook.
So, but here, even if we substitute n equals 0, then for the constructive one, like we're never going to get y is equal to 0.
How to get the width of the central maxima? Any thoughts on that? No? Okay, suppose this is the point where the first minima is coming. And this is the point where first minima, two first minimas will be there when you put n equal to plus minus 1, right? So can I say distance between the first minimas is the size of the central maxima? Make sense? So y is equal to lambda d by a is the first minima and minus lambda d by a is also first minima. What is the distance between them?
2 lambda d by.
Correct. So the fringe width of the central bright is 2 lambda d by a. Okay. This is the fringe width of the central bright. Now tell me fringe width of the other bright fringes. A fringe width of any bright or dark. Distance between two consecutive dark fringes is what? Put n equal to n and
Lambda d by a.
lambda d by a, right? So central maxima width is 2 times the normal fringe width. Okay, remember this. Not only that, intensity of central bright is highest, and intensity rapidly goes to 0, rapidly decreases as we move away from the center. Away from the center. Can anybody tell me why this happened? Anyone? No one? No one?
So is it because like the central point is the only place where no destructive happens? As you go upward, more and more destructive start happening.
No. Constructive interference will happen at the point, just like Young's double slit experiment. In Young's double slit experiment, every bright fringe, including the central bright, has the same intensity. But here it is different. The reason is single slit experiment is the fight between ray optics and wave optics. Okay, so what happens is that if ray optics is dominating, then entire light should not go beyond these two rays. Okay, all the light should be contained in this zone only. All right, but the ray reaches that side only also because of wave optics. Fine, but that can't be taken away, that it behaves like a ray also. So major portion of the light remains there only. Okay, and at the center it is brightest because of the wave optics. Fine. So this is the reason there is no formula as such to find out the intensity. Okay, can you show a photo of experimental setup? No, experimental setup, I'll not show the photo. I'll show you the fringe photo. Okay. This is what it is. The front slide, if you remember, this one is the diffraction pattern. You can see here, the central bright is, it is, the width is very high and it is brightest also. Intensity is rapidly decreasing as you move away from the center. And fringe width, you can see, remains same. Okay, fringe width remains same after central bright. But intensity is going down. After every bright, there is a dark fringe. Every bright, dark fringe is there. Okay, so this is the outcome of the diffraction pattern. Okay, this is what you wanted to see, Ruchir?
Yes, sir.
Okay. All right, so let's proceed further. If you plot a graph between the intensity and distance from the center line, you will get a graph like this. The central bright will be brightest. This is on the y-axis intensity, on the x-axis is the y coordinate. Okay, like this, and then the intensity rapidly decreases. Like this, you can say. Fine. This is the intensity versus y graph. There is no mathematical expression as such, and you can see that the width of the central bright is double the width of other brights. Anyway, so now that we have learned about the diffraction, okay, let's quickly summarize the difference between Young's double slit experiment and single slit experiment. Why we are writing it? Because many times in your board exam, this question comes. Write down comparison between Young's double slit experiment and single slit experiment. Okay. All right. So, what is the first point? What do you think?
So there's two
slits,
slits
one
and that
slit.
one slit.
Okay. So, Young's double slit experiment is the outcome of superposing two waves. Okay. Whereas the single slit experiment the outcome is superposition of family of waves. This is the first point of difference. Second one, in the interference pattern, interference patterns has number of equally spaced bright and dark fringes. Okay. Whereas the diffraction pattern has the brightest spot at the center? Okay. Not only that, the width of the central bright is twice the width of other bright fringes in diffraction pattern. Fine, these are the basic differences. And then mathematically, you can see that y is equal to, or okay, first you write down, then I'll tell you what this means. Write down at an angle of lambda by a, you'll get first dark in diffraction. Okay, whereas at an angle of lambda by d, you'll get first bright in Young's double slit experiment. Okay, now I'll quickly tell you what does this angle actually means, because this angle will keep on coming in your whenever you solve problem. Also at times they will tell you what is the angle subtended by the third bright, or what is the angle subtended by the fringe at the center, and so on and so forth. Okay, let's see. No doubts, right? It is all theory anyways. I don't think there
So I have a doubt.
Ah.
So why didn't we consider the same reason in Young's double slit experiment, that ray optics also?
It is there, no? It is there, but then over there, what happens is you have two slits. Fine. So whatever happens there because of ray optics, that get nullified by whatever happens there. So there is a symmetry over here like that. Okay. So I mean, you can debate. Even I can debate on it, but the reality is that the ray nature of the light gets suppressed in Young's double slit experiment because of this kind of symmetry. Okay, whereas in the single slit experiment, it was a single hole. So from a single hole, a single beam of light comes in. So you cannot ignore the ray nature of light. There is no 100%. It is not black or white. Okay, it's like a gray area. There's interference, Young's double slit experiment, and diffraction. There will be little bit of ambiguity, but then the way you study it is as per your syllabus, is the way whatever we have discussed here. Okay, till now no scientists have been able to convincingly tell the difference between diffraction and interference. Also there is an ambiguity. Okay.
Yes, sir.
That's a problem. The light has a dual nature. So at the same time it behaves both light and ray, but sometime prominent is ray, sometime prominent is wave. Whereas in single slit experiment, both are equally prominent. We cannot ignore a beam of light coming in from a hole as a ray. All right, guys. So let us discuss this experiment here. And one more thing, I think Rajdeep has asked very good question, is that in Young's double slit experiment also, if you consider a wavelength which is very less, okay, let's say you start using X-ray in a Young's double slit experiment which has the slit hole, the width of the slit is very less. Let's say this is like 10 to the power minus 5 meter only is the hole of the slit. Then X-ray, since wavelength is so less, you will not be able to observe interference pattern. you will just see the ray nature of the light. If you pass X-ray, you'll see two spots there because of X-ray. Because the ray nature is getting prominent, all right? So you need to make sure that the wavelength is not very, very less. If it is less, you need to decrease the opening of it. Otherwise, it will just pass through the opening as a ray, and the ray nature will be prominent. So yes, all that do happen, Rajdeep, but still, we are not getting into those kind of details. Otherwise, it will confuse more.
Yes, sir.
All right. So, so I was talking about the angular width or the angle. The last point. Look at it again. This is the last point. At an angle, first dark. At an angle, this first bright. So, what is the angle? That is what we need to discuss. So, if you consider a Young's double slit experiment setup, over here, we anyway are assuming that the distance y is very less. Okay, so if two rays are meeting here, and let's say this is your y, we need to find out what is the angle this point subtends at the center. Then I will connect a center line over here. All right, I need to find what is this angle, theta. And since theta is very less, as y is less and d is large, I can say that theta is approximately equal to y by d. Getting it? Is there any doubt? It's like arc length divided by the radius. Fine. So for nth bright, the y is n lambda d by d. You can see one important thing here, that if you change the value of d, if d increases, the location of the bright fringe moves up. Okay, so if I just move the screen away, the y will change. So the thing is that whenever we're studying the interference pattern should depend on the property of the wave only, and what is happening at the slit. It should not depend on the capital D. So y is not a proper parameter to study. Instead of studying y, it will be better to study angle theta, because if you shift the D that way also, then also angle theta won't change wherever the nth bright fringe will be there. So that is the reason why angle is introduced. So if I substitute the value of y over here, I will get theta to be equal to n lambda by small d. Okay, and similarly you can find the angle in the case of the single slit experiment as well. Fine. There is something called the angular width of the fringe. Angular fringe width. It is nothing but the angle subtended by fringes at the center. Okay, so fringe width is beta divided by d is angular fringe width. Fine. You can, rather than calling it theta, you can call it alpha. Beta is lambda d by small d, that divided by this. So the angular width is lambda by small d. Any doubts till now? Anyone? No doubts? Okay. Now here is one question to all of you. Tell me one single slit experiment or single slit setup that you are using every day?
Torch.
Say it again.
Torch.
Torch.
So our eyes are single slit.
Our eyes are single slit. Very good. So you can see that our eyes, I mean, some of you may argue that eyes are double slit because we have two eyes, but the fact is that even camera is single slit, yes. But the fact is that both the eyes have two different screens. Okay, one eye has one screen. So it is a single slit. A single slit, the practicality of single slit experiment is multifold. I mean, double slit you don't observe in nature just like that. But single slit is there everywhere. Even our eyes are single slit. Ruchir, what do you mean by torch? Torch is not something to be used to, observe something. Torch is something to throw the light upon. Okay, there has to be a screen somewhere. Camera captures the light. Our eyes capture the light. Torch doesn't capture the light. Okay, so if that is the case, that our eyes are the single slit experiment, then on our eyes retina, there has to be a diffraction pattern. Okay, and this diffraction pattern is one of the biggest deterrent in increasing the resolving power of our eyes. All right. So the next topic, all of you write down resolving power of optical instrument. Our eyes are one such optical instrument. Okay, so here I'll tell you one thing, that when the diffraction pattern is observed, let's say you are observing a point object, light from the object should reach to your eyes, right? So when the light from a point object reaches your eyes, we can say that since light is a wave, there should be a diffraction pattern on your eyes. Okay, so rather than creating a sharp image, it'll create a fringe pattern, and at the center you will have a brightest spot. So the image of the point object will occupy some width on your eyes as part of your central bright location. What I'm trying to say here is that suppose this is your eye. Okay, you're observing a point over here. What will happen? Diffraction pattern will be there. So rather than a point, you will have a diffraction pattern that will be there on your eye screen. But the good thing is that intensity of the other maxima is almost zero. But the intensity of central bright you can't ignore. Okay, so the point object has spread its light in this zone. And suppose you are observing another point object which is very close to that point object, and the image of this also create a diffraction pattern. So if central bright of this light from this object coincides with central bright of that object, you will not be able to observe them as two separate objects. So two bright fringes will just merge. You'll feel as if only one object is there. You'll not be able to make out any difference. Fine. The day-to-day life example is when you look at the pixels of the television, you're not able to tell that there are pixels there, right? Because your eyes are not having proper resolution. Fine. You're not able to make any difference out that there are two different pixels separated by some very small distance. Fine. Anyways, it will be more clear when we take up the more example. Now tell me one thing. Can anyone try to define what is resolving power? I mean, can you explain a little bit about it, what it is? Based on whatever discussion we had just now, can you try explaining it or try to quantify it, right? Anything that we learn in physics, we need to put a number to it and define it, what it is. No one?
So the smallest size of an object a particular distance from us, which we can see clearly,
Smallest size of one object.
which is at a particular distance from us, which we can see clearly.
That is not resolution actually. That is not resolution. You'll be able to see that object at whatever distance it is. If light from the object is able to reach your eyes, you'll be able to see it. Okay. Probably your eyes may not be sensitive to very, very small intensity. Okay. But that is different. That has nothing to do with the resolution.
So is it distinguishing between 2-3 small objects kept next to each other?
Write down. It is the minimum distance between 2 point objects for an instrument to distinguish between them. To distinguish, does it make sense?
Yes, sir.
But have you ever went too close to the television and have you ever been able to find out that television is made up of pixels from your eyes only if you come very close to your television?
Yes, sir.
Right?
Yes, sir.
So,
Even for laptop.
so minimum distance changes. If you come close, you're able to distinguish, right? But when you're very far away from television, you're not able to distinguish. So this definition is not correct. It should not be minimum distance. Then what it is? And what I'm trying to say is that
Minimum angle.
Correct, the angle. These 2 points, if you look at from very far away distance, these 2 points, you'll not be able to find out that they are two different points. But if you come close to it, you'll be able to find out. Okay, so it has to do with the angle. Okay, our eyes or resolution is more. It is the resolution. Our eyes are more sensitive to the angle, okay, rather than the distances. So if you're very far away, let's say this distance, the angle made by these two objects is very small, okay? So you'll not be able to probably find a difference that there are two objects. But if you are close, then same angle becomes much bigger. This angle is a lot bigger, fine? So you can name it as alpha and this as theta, fine? So the definition has to be like this. Minimum angle, write down. Minimum angle, the 2 points subtend at the instrument. Your eyes are an instrument, okay? At instrument to distinguish. Don't try to mug it up word to word. It is not a definition, it is an explanation, okay? To distinguish between them. Okay, now if if the minimum angle for which you can find out that there are two different objects, if minimum angle is reduced, resolution is reduced or increased?
It's increased.
Increased.
Increased. Fine. Remember that. Okay. So minimum angle, if it is lesser, your resolution is higher. Fine. So if you are able to distinguish even for the lesser angle of theta, it means that the resolution is higher. Okay. Fine. So in order to basically understand the resolution, we are making one small assumption, which is very reasonable assumption. Look at the central bright, you look at it, how bright it is. If there are two images on this central bright, will you be able to identify that there are two images? There is no chance that you will be able to identify anything falling, any extra light falling on the central bright. You'll not be able to find out what that light is about. Fine. So the assumption goes something like this. If the images of two objects fall on same central bright, then we cannot distinguish between them. Okay, so this is sort of assumption and a very reasonable assumption. So our entire mathematics revolves around this assumption only. The distance, minimum distance, can we say minimum angle? Yeah, that is what. Understood here? Okay. All right, so let's do some mathematical analysis of how can we define the resolution of something. All right, so here it is, all of you. Draw a convex lens. Ultimately, the light has to converge. Okay, when you're looking at a faraway object, the light is coming parallel to your eyes or to the camera. So camera should have a convex lens. Fine. Whenever we talk about resolution, we are assuming light is coming from infinity. Getting it? Because resolution makes sense for the faraway objects only. So we'll assume it. Okay, so suppose you have a faraway object, point object on the principal axis, where the image will be getting formed?
Focus.
At the focus. Will there be a point image? Sharp
Yes.
pointed image? No.
Why?
The reason? It is wave optics here. Of course, intensity will be highest at the center and then it will just die away. So your eyes will probably feel that the image is in this much distance. You'll get a circular image, light will be dispersed from here to here. Okay, but I'm drawing it so big, but this is not how big the problem is. Okay, so still the distance will be very less only, but what I'm telling you is that it will not be a point size. Okay, so that's the reason why I'm drawing it bigger. This distance has to be f. This distance is f. Now, if I draw it, the front view of the fringes, if I draw the front view of the fringes, you'll see how it looks like. You will have a central bright. Central bright. Draw it with me, all of you. Circular central bright like this, and you can say there is another bright fringe, but that bright fringe intensity is very less, but just for the sake of it we are drawing it. Okay, so experimentally it is found out, experimentally, empirically, and various other means, not part of our curriculum, the derivation of it, we'll assume it the way it is. Experimentally, it is found out that the distance, this distance, the size of the central bright, the size of the central bright is given as 1.22 lambda f by a. Okay, this is the diameter of the central bright. I hope this thing is clear. One point object will create an image like this, which has a central bright. The central bright has this much wideness. Okay, now you are watching another point object, let us say. Okay, another point object is also at infinity. Let's say the rays are coming at certain angle. So from the optical center, it will pass through, and this angle is, let's say, delta theta. So angle between the two objects is delta theta. Fine. But won't it be 2 lambda d by a? No, Ruchir, no. It is not that. Okay, it is not a single slit experiment. It is a lens. Okay, and lens is not a. I mean, there are multiple things. First of all, it is lens. Second, the thickness is not uniform, and forget about. I mean, just do not use that concept of single slit experiment here.
Yes.
If there is a diffraction pattern through a lens whose, that I haven't told you, this distance whose aperture is 2a, this distance is 2a, okay? The diameter of the lens is given, this is 2a. If there's a diffraction pattern from a convex lens of aperture 2a, then the size of the central maxima is this. Our eyes also have a convex lens. So I have two objects, object 1 and object 2. They are subtending delta theta angle. Delta theta is extremely small. Okay, that is why we are talking about resolution here. So can you tell me, I mean, the image will be here. Ideally, this is the center of the central bright fringe of object 2. So this distance, the distance between the centers of the image, this distance will be what? Anyone? In terms of angle? Jaldi bolo, quick.
So f delta theta.
F delta theta. Okay, this is arc length divided by the radius, which is f. So f delta theta. Fine. So if f delta theta is less than half of this, because I mean from here you're considering, okay, this is the half of it, is less than 0.61 lambda f by a, which is half of that, then I can say then the images, image 2 falls on central bright of image 1. And hence, we won't be able to resolve. We won't be able to resolve. So we will think that as if there is only one point object. So when you look up the sky and look at the stars, you may at times feel that there is only one star at a location, but if you increase your resolution somehow, you'll identify that there are tens and hundreds of stars at the same point. So this is what is happening actually. Because of the diffraction, our resolution of eyes are limited. Blame it to the wave optics. So the minimum angle, let's say, is theta minimum, should be such that it is equal to 0.61 lambda f by a. So delta minimum comes out to be how much? 0.61 lambda by a. Fine. Now you want delta minimum to be as less as possible. Then your resolution will be better. So if you want your delta minimum to reduce, what you can use, what you could make changes? Anyone?
So you can change A, make it bigger.
You can have a bigger lens, right? You can increase the aperture of the lens. That is what I told you earlier. The size of the objective in the astronomical telescope is huge to make sure the resolution is high. Okay. What else you can do? You can decrease the wavelength, right? But can you do so when you're observing heavenly objects? The wavelength is fixed. Whatever wavelength they are throwing out to you, that much wavelength only you will receive. But suppose you are observing microbes or let's say viruses, bacteria, then you can throw light. Your light source need not be microbes. Fine. So when you're throwing light to these objects, you can increase the frequency or decrease the wavelength to increase your resolution. Fine. So you might have heard about the X-ray, uh, what is that? X-ray microscope. Have you heard of it? Have you heard of electron microscope?
Yes, sir.
Electron microscope, the electron beam has very less wavelength, so that actually resolve it. Okay. Yes, theta minimum doesn't depend on f. Okay. So you can resolve it better if you increase or if you decrease the wavelength. But that is not possible when you're observing an object which have its own light. But anyways, this is what it is. So there can be a numerical based on this concept, something like this. Okay, please write down. There is a situation like, for example, a truck has these two headlights. The distance between them, these two headlights, the distance is, let's say, small d. Okay, if that is a distance between them, and the wavelength that is coming out from this headlights of the truck is lambda, fine. You need to find out the minimum, or you can find out the maximum distance d for which you can clearly see that there are two headlights. Clearly see both headlights. Fine. Assume the aperture of the lens of your eyes is 2a. Now do it. Okay, straightforward. So minimum angle theta is small d by capital D, right? So if there are two light sources at a distance of d, the angle subtended will be small d by capital D. Fine. This should be equal to 0.61 lambda by 8. Fine. So from here, I mean, it's a direct substitution numerical, but many times people forget that you can solve numericals by using this formula. So I thought I could just tell you that. So D is equal to AD divided by 0.61 lambda. Okay, so like this, you can attempt this question.
So,
Hmm.
so like, is the like resolution of all these like devices, like phones, laptops, and stuff, is that in any way related to this?
You're talking about pixels,
Yes, sir.
HD, Super HD, Ultra HD.
Yes, so all the 4K, 1080p, all
Uh,
that stuff.
all that is actually, I mean, I don't want to make fun of it, but then yes, it is practically useless when you go to the shop to purchase Ultra HD, let's say. The what they do is that they increase the brightness and contrast of Ultra HD, and the HD television, the colors are decreased. Some internal setting is done, so they will make you believe that Ultra HD looks much better than the HD, but in reality you'll not be able, your eyes are not capable to make out any difference because pixels are so close, and you are anyway not going to watch the television sitting at just 1 centimeter away. Fine, so it is all useless until and unless you are zooming in, which is like absurd. You'd never zoom in the television when it is running live. Fine. So yes, it is not required, but at the same time, if there are too much of details, which happens very rarely, that a picture or a landscape has too many details. After every few pixels, the color is changing, or after every 2 pixels, some small spot is there here and there. Then probably it is better. But 99.99% cases, your HD television or HD ready television is as good as your Ultra HD or Super HD television. It's practically useless.
Yes.
All right, guys. So we'll take a break, or should we continue?
So break.
Break. Okay, we'll take a break. Right now it is 6:04. We'll meet after 15 minutes. 6:19. Bye for now. Okay, so I hope all of you are back. Just few seconds. All right, so let us continue. Fine. So we were talking about the diffraction till now, and we have discussed about the resolution power of optical instrument that comes because of the diffraction pattern that is observed by the light, and the reason why diffraction is observed is because of the wave nature of the light. Okay. Now, when we have started the diffraction, we have also mentioned that the diffraction is most commonly observed phenomena, and we also discussed that in diffraction both things are observed. The ray nature as well as wave nature both are prominently observed. How can we say that? Because most of the light will reach the center of the screen because of the ray nature of light. So intensity of the central bright is highest because of the ray nature of the light. Fine. And intensity light bends, and there is some intensity away from the center also. That is because of the wave nature of light. Okay. So we are going to define the validity of the ray optics by using diffraction only, or by using single slit experiment only. Okay, write down validity of ray optics. Today's plan is, that once we are done with the theory, we'll solve some advanced level numericals. Okay. You have to do those advanced level numerical even though you're not preparing for advanced, because same advanced level numerical, part of it can come in mains level numerical. Okay. So looking at a numerical, you can't say that this will never come in mains level. Okay. So validity of ray optics. This is what you have to do. Suppose you have a single slit experiment. Whenever you are doing any experiment, there will be single slit somewhere. There will be a screen somewhere. There will be a small opening somewhere. If not anything, your eyes are single slit experiment. Okay. So this is your screen. Light will come. This is your center line. So basically, if light is a ray, it should continue going like this. And this is how it is. This is 100% ray optics. Fine. But if light is a wave, it should bend more and more. It should bend more and more like this. Fine. So the amount of bending, this distance, okay, based on that distance, we can say whether we should use the concepts of ray optics, or you can say whether the ray optics is prominent or the wave optics is prominent. So either too much of dispersion or too much of bending of light like this, you can say that wave optics is prominent. So let us try to define like this. Let's say this angle is theta. Okay. So this is the position of the, let's say, first dark fringe. First dark. Fine. And this is the deviation. This deviation is, let's say, delta y. Delta y. So, it is assumed that if delta y becomes more than the opening of the slit, they say this opening is A. If deviation from the original part, delta y, becomes more than A itself, you can safely say that wave optics is prominent. Wave optics is prominent, or wave behavior is prominent. Okay. And if this is less than A, then you can say that the ray optics principle dominate. Okay, now you can debate why A, why not A by 2, why not 2A. It is like asking a question like why 1 meter is this much, why 1 kg is this much. You have to assume something. So this is how it has been assumed. All right. Now, can you tell me what is the value of delta y? Delta y in terms of theta and A. This is the value. Not A, sorry. This is D. This is D, right? Achha, leave delta y. Tell me how much is theta? Theta is what? The angle subtended by the first dark. How much it will be?
So tan inverse of y by d.
First dark, what is the angle subtended? Again, think over it. The location of first dark is how much? Lambda d by A. Okay, so the angle is y by d, which is lambda by A. Okay, so theta is lambda by A. Fine. So delta y is theta into d. So lambda d by A. Okay, so when this becomes equal to your A, then you can say that this is a critical distance beyond which you will have wave optics. This distance is called the Fresnel distance. Which distance I'm talking about? The distance capital D, which will come out to be equal to A square by lambda. Okay, so if your screen is beyond that distance, you need to assume wave optics is prominent. If your screen is lesser than this distance, your ray optics is prominent. Okay, this is called the Fresnel distance. Any doubts?
So isn't y the distance from the center? And here we took a different delta y.
Theta is lambda by A. Theta into D is your distance delta y, like this.
So but here we said y equal to lambda d by a. So isn't y from like the center blue line till the top?
You're saying from here to here?
Yes, isn't that y?
Yes, I can understand what you're trying to say, but then we have found the distance by using the approximations and assuming that theta is same. Okay, so this delta y comes out to be theta is lambda by A, and theta into D is your deviation. This deviation I'm equating it to be A for Fresnel distance.
Okay, sir.
For application of ray optics and wave optics with respect to D.
Could not hear you properly. Say it again.
So, could you repeat the condition for when we use wave optics and ray optics with respect to D's?
If your screen is lesser distance than the Fresnel distance, ray optics is prominent. Otherwise, wave optics is prominent. Okay.
Thank you, sir.
Ruchir Parekh, I can understand that doubt. Okay, but this is how it is derived. All right. So yeah, there is some confusion related to that. But a square by lambda is your Fresnel distance. There is no confusion in that. Okay.
Okay, sir.
All right, guys. So let us get into the last part of the chapter. It is called polarization. Okay. Write down polarization. Have you heard of polarization ever with respect to light? Polarized light, have you heard in chemistry? Where you use
Yes,
it?
plain polarized light, stereochemistry.
Stereochemistry. So you are, when you have to identify dextrorotatory or levorotatory DNL isomers, you are using the polarized light. So if one isomer rotates towards the right, one type of isomer, if left, other type of isomer. So what happens is, why it is so important to identify which isomer these organic compounds are, because our body reacts to dextrorotatory and levorotatory in completely different way. So one isomer could be acting like a medicine, another could be acting like a poison. So you need to be very careful which type of isomer you're giving to the patient as a medicine. Fine. So that is the main utility of the polarized light. But when we are talking about physics, we don't need to worry about its application. We are talking about how it is produced and what it is. Fine. So polarization is a phenomena exhibited by the transverse wave only. Exhibited by the transverse wave. And since light exhibits this behavior, polarization, we can polarize the light. It proves that light is a transverse wave. Fine. Now let's talk about what is polarization. Okay. So if you would have seen the electromagnetic wave as in its picture, let me show you EM wave. So this is the EM wave, and you can see here EM wave has one component of electric field and other component of, and the another component which is the blue component, that is a magnetic field. Okay, so electric field oscillates perpendicular to the magnetic field. Fine. Now if I say that this is my x-axis, this is my y-axis, and that is my z-axis, which plane electric field is oscillating? What is the plane of oscillation for electric field?
So YX.
XY axis, right? Magnetic field is in XZ axis, fine. But do you think that the light received from the sun will be that systematic, as in entire electric field will be oscillating in a single plane and magnetic field will be oscillating in another plane? Will it be like this, or it will be random? Electric field will be oscillating in every random direction, and corresponding to it magnetic field will also oscillate. Do you think it will be systematic like this or random? It'll be
I think
random, right?
random.
I don't know
Random,
why
sir.
there is so much to think. Fine, it has to be random. So there should not be any preferred plane in which electric field should oscillate. So electric field will oscillate in every possible plane, and for every electric field, magnetic field will oscillate in the perpendicular direction. So every direction electric field also oscillate, every possible direction magnetic field also oscillate. So if that is the case, if electric field oscillate, please write down, if electric field, so I'll be talking about electric field, corresponding same thing will happen to the magnetic field also. Okay, if electric field oscillate in more than one plane, more than one plane, then light is unpolarized. Okay, so opposite to this definition, if electric field is oscillating in a preferred plane always, then that is polarized light. Fine. So did you guys learn how to polarize a light in chemistry? Have you learned about it?
So we had to pass through a Nicol prism, I think.
Nicol prism, right? You pass through a Nicol prism. What happens is that there is crystal lattice in the Nicol prism. There is atomic planes. The distance between the atomic planes is so less, and there, I mean, it is not as simple as that. What I'm telling you, there are other details to it. So what happens? Distance becomes so less that it only allows the oscillation parallel to the uh, space to pass through. What I'm trying to say is that suppose you have this is, let's say, a Nicol prism, fine, wherein you are putting the slits. This is slit, or you can say interatomic distances. These are the slits. Okay, these are the slits which represents the opening for the light to pass through. Light can only pass through these openings, and there is no other place for the light to pass through. Okay, so if light passes through this opening, when the light comes out, the oscillation of electric field will be only in the perpendicular direction, only in the direction of these slits. Fine, that is the direction of electric field, and perpendicular to it will be the magnetic field that will come out. Fine. So when we represent an unpolarized light, we show it like this. This is like oscillation in the plane. I mean, this is this way we can show the electric field is oscillating in the plane. The dot represents oscillation perpendicular to the plane. Oscillation perpendicular to the, mute yourself, perpendicular to the plane. Okay, so these are the two polarized light. When you show only this, it means polarized in this plane. When you show only dot, it means polarized in the perpendicular to the plane direction. Okay, but if you show like this along with a dot, okay, this is the representation of unpolarized light. So every time we'll not be drawing waves like this to represent unpolarized light or polarized light. It becomes uncomfortable. Okay, so basically what is happening is that this polarizer could be whatever it is, Nicol prism or whatever it is. We, like I said, we are calling it a polarizer, or you can say Polaroid. Okay, when an unpolarized light passes through it, unpolarized light is arrow with a dot. What comes out is polarized light, which is oscillating in the plane of the slit. Is this clear to everyone, whatever we have discussed just now?
Yes.
Okay, this is, I think straightforward, much simpler than whatever we have done till now. So this is how you polarize the light by using Polaroids or polarizers. Okay, now there is a study of what will happen, to intensity, because eyes, you know, our eyes are sensitive to intensity only. Our eyes don't care electric field is oscillating in which direction. We'll not be able to notice it, right? So our eyes are sensitive to
So, is there like, can you give an example where, once the light gets polarized, it oscillates perpendicular to the plane?
Why not? You just rotate the Polaroid, then pass the light through it. The light that comes out will be always in the direction of the slit. Depends on what angle you're keeping the slit. Rotate it.
Okay.
All right. So our eyes are sensitive to the intensity. Fine. So we need to see what happens to the intensity. That is much more meaningful for experimental purposes. Fine. So let us discuss that. Just wait a minute. So suppose you have a polarizer like this, and you have the slits. All of you draw with me. Don't wait for me to finish and then you start copying it. This is the slit, and the light that is coming in is unpolarized. That comes out is polarized, that we have already discussed. Now we need to discuss what happens to the intensity. Okay, so if the intensity of the incoming wave is I naught, okay, this is I naught. Okay, what will be the intensity of the outgoing wave over here? This is unpolarized light. It oscillates in all directions. Okay, if you want to actually show it, the unpolarized light, this is the better representation of an unpolarized light. It oscillates in all directions like this. But for the sake of simplicity, we are just showing it with a dot and arrow. Okay, so if this is the case and intensity over here is I naught, how much will be the intensity over here, the other side? Tell me. No one?
So can we say that like we only take the component of the electric field in this plane, so we can just take like the cos of the angle that it makes, or like if we convert it into vector form, then we only take the component in the plane of this one, so the x and y component.
I didn't get you. I'm asking you about what is the intensity on the other side.
It has to be lesser, so
So you can't quantify it? Is that what you're saying?
so if we had like the so like if so like I think we would need to know the magnitude of the electric field.
Okay. So, I can understand there will be some confusion here and there, but here is the thing, suppose the oscillation is like this, it will make some theta angle. So its oscillation in that direction will pass through and in that direction won't pass through. So a component you have to take, okay? When you take the component of the oscillation, okay, I'm saying that amplitude component will pass through it. So a cos theta of everything will pass through it. Intensity is cos square, amplitude is square. Then you take the average of it, average of cos square is half. So what comes out is half of the intensity. Fine. So you just remember it that when unpolarized light of intensity I naught passes through a Polaroid, half of the intensity will come out. Clear?
Yes, sir.
Okay. Now, if I'm putting another Polaroid here, fine. If I'm putting another Polaroid over there, which has slits like this, then what will be the intensity on the other side?
0.
Correct. It will be 0. Okay. Intensity will be 0 over here. The angle between these two Polaroids is pi by 2. Or we can say that they are the crossed Polaroids. I don't know how many of you are in the into the photography and use Polaroids in the photography. Okay, but Polaroids are used quite often in photographing things, and usually you have two Polaroids. One Polaroid will polarize it, other will manage the intensity of the light. Okay, so what happens is, I'll just give you one example of it in the photography, and I think I might have discussed it already. Suppose there is an object whose photograph you want to take. Fine, this is your camera, let's say. The light comes like that, hits the surface, part of it will be reflected, part of it get refracted, and then both the lights you capture. This light also you capture, and the light from the object also you capture. So you get a blurred image of this, because this light, when you capture, you're capturing the image of the surface or interface also. So by using Polaroid, you can reject this light. You can reject it. If you somehow reject this light, you are only capturing the light coming from here. So much better image will be formed. Okay, and you will be able to see that images by using Polaroids are much better in terms of color, depth of colors, and contrast and everything else. Okay, so we'll also discuss how reflection, how that affects the polarizing behavior of the light. Okay, right now we'll continue with this discussion. I thought I just tell you that you can use the Polaroids not only to understand the isomers, but in the case of the camera as well.
So how exactly does the reflected light get rejected?
I told you now, I will be discussing it. Okay, fine. So let's continue from here, and let us assume that you have a polarizer here and another polarizer here. Now they are not crossed. Okay, you have a polarizer like this whose slits are vertical, and the other polarizer is something like this. Okay, the angle between these two slits is theta. All right, so if an unpolarized light is coming from the left hand side and has intensity I naught, let's say this intensity is I naught, you need to tell me intensity over here, how much it is. This time it won't be 0, right? How much it is?
I naught by 2 cos theta.
Cos theta or cos square theta?
Cos square.
Cos square, sir.
Correct. So this will be a polarized light. I naught by 2, and over here the situation will be like this. You'll get a polarized light which is rotated like that now. But intensity will be reduced. I naught by 2 cos square theta. So remember this. If an unpolarized light passes through a Polaroid, intensity will become half. But if a polarized light passes through a Polaroid, it will become cos square theta times. Okay?
So I have a
So
question.
why cos square?
Why cos square? Because you don't take component of intensity. Intensity is energy. You take component of the vibration or amplitude. Amplitude square is intensity.
Okay, fine.
All right, so let's take one numerical on this and then we'll proceed further. Here it is. All of you draw this. Now you have 3 polarites. I am drawing polarites as if it is in the plane, but in reality they are perpendicular to the plane. Okay, the light is in the plane, but we can't draw perpendicular to the plane, so that's why we are drawing it like this. So you have the slit of the first polaroid and the second, and the third one. The slits are crossed. Okay, this one. And that one, they are crossed. Okay. And this one, it's like that. The angle between the first and the second one is theta. First and third one is crossed. So an unpolarized light passes through the first one. Okay, this is an unpolarized light of intensity I naught. You need to tell me intensity over here, how much it is.
So should we type in the answer or just say it?
Type in karo. Don't speak the answer. Don't tell the answer. Done? Anyone? Many of you have answered. All right, great. So I can see many of you have got it. So over here, the intensity will be how much? I naught by 2.
By 2 cos square.
I naught by 2. Why cos square theta here?
No, sir. The board was lagging. I couldn't see it.
Are you sleeping?
No, sir. Like my internet is a bit unstable, so your pen was somewhere else.
Okay, no, I thought you sounded sleepy. Okay, here the intensity will be I naught by 2
cos square theta.
Cos square theta. The angle between this and that is theta, right? Over here, what will be the intensity? I naught by 2 cos square theta into cos square of angle between these two. What is the angle between these two?
90
90 minus theta.
90 minus theta. See how simple it is? Cos square 90 minus theta. So you'll get I naught by 2 sine square theta cos square theta. If you want to further simplify it, it will come out to be I naught by 8 sine square 2 theta. Okay. I mean,
So why do we multiply?
what do you mean?
Why do we multiply it with cos square 90 minus theta again?
See, that is what I said. You're sleepy. See, what happens is, if this is I naught by 2, you multiply cos square theta with whatever was the intensity before.
Yes, sir.
Here, what is the intensity? This. So that into cos square of 90 minus theta, I have to multiply. Same thing we are using. Instead of I naught by 2, I have to use this.
Yes, I understood.
Okay, woke up.
Yes, sir.
You said, yes, I woke up. You were sleeping before.
No, sir.
All right, so this is the answer. And, I have not seen many numericals on this topic, but if it comes, there's nothing more than this. So you'll be able to solve it. So let us move to the second part of this topic. So polarization is done by, till now we have learned that it can be done by using polarites like Nicol prism and other, some objects. Okay. Now we are going to see two different ways in which polarization can be observed. So C.V. Raman, who was an Indian scientist, he came up with one of the ways in which we can get a polarized light, and he got a Nobel Prize for it. So the derivation of any of these methods, as in why light gets polarized, is not part of our study. If you really want to understand, probably you need to go through all the works C.V. Raman has done and do your PhD and all that. So we are not interested in that as of now. So we'll just take the observations here. Okay, write down polarization by scattering. I hope you remember what is scattering. So what happens is, when the sun emits light, it is unpolarized. Fine. This unpolarized light, let's say, get absorbed by a particle. Okay, this get absorbed by the particle, and then this particle will emit light in all directions. Fine. In all directions, this particle will emit the light, and it is observed that the light which is perpendicular to the original direction is polarized. Okay, this light that is perpendicular to the original direction of incident. Okay, so you can say this is scattered light that is polarized. Scattered polarized light. Fine. So see how simply you can get a polarized light because of scattering. Okay. So this is polarization by scattering. Next is polarization by reflection. So this will answer your question on the camera example that we had taken. Write down polarization by reflection. Okay. All right. So what happens is, this is also an observation here. So if there is this is an interface, let's say, on which light is getting incident. Okay. If the light gets incident like this, part of it will get reflected and part of it will get refracted. Fine. So I'll draw the normal. This is the normal. Fine. Refractive index is, let's say, mu. This is reflected and this is refracted. Okay. So if angle between reflected and refracted is 90 degree, if reflected and refracted angle is 90 degree, then it is observed that the reflected light is polarized. Reflected light is polarized. Okay? This is what is observed. We are not debating why it is like this. Now, if this is true, and refractive index of the medium is mu, you need to tell me at what angle of incidence theta should light be incident so that I will get a polarized light. Find out angle of incidence theta. So what is the angle theta? Okay. No, here you think you did something else. Vikas got it, Ruchir got it, both the Ruchirs got it, Mahit got it, Mahit Nandan got it. Alright, so now tell me, if this is 90 degree, this is also theta, right? Because of reflection, law of reflection. What will be that angle? This angle will be what?
90 minus theta.
90 minus theta, because sum of all these angles should be 180 degree. This one, that one. So now I can use Snell's law there. So 1 into sine of theta should be equal to mu into sine of 90 minus theta. It is simply Snell's law. So tan of theta comes out to be mu. Okay. So this is called the Brewster law. There is a name also. Someone has to take credit. Brewster law it is. That if you incident at this angle, which is tan inverse mu, the reflected ray will be polarized. So if this is the reflected ray, you are suppose looking at the object using camera and you change your angles in such a way that incident and reflected, they are making 90 degree. You have to keep on monitoring the angles, or you just have to do trial and error. Then the reflected ray at some point in time will get polarized. And then using polarizer, you can have a polarizer which is making 90 degree with the direction of polarized reflected ray. So that reflected ray will be rejected then. Okay, so like this you can filter out the noise. All right, guys, so this is what the entire chapter is all about. We are done with the wave optics. Congratulations. This completes 40 to 45% of your 12th curriculum. We'll be soon finishing your 12th curriculum, and then the main thing will start, which is daily problem practice. So daily we'll be meeting up after October 1st week. Every day 4 hours of problem practice we have to do, because we believe that January JEE mains is your best shot. If you do well in January JEE mains, where everybody else is relatively lesser prepared, it will be easy for you to do better, okay? Because everybody else is lesser prepared. So it is not an amount of preparation that matters. It is relative preparedness that will determine your rank. So you'll naturally do better in January, and you'll have, better peace of mind, and you'll be looking at something else after January. You'll be probably preparing for bits for JEE Advanced, for every other exam that is there. NEET is there. Then so many exams are there. Nicer, ICER, so many things. But if you don't do well in January JEE mains, then on back of your mind while preparing for board exam or nicer, ICER, JEE Advanced, so throughout this pressure will be there in your head that right now your place is not secured. So that is the reason why we are emphasizing more on doing well in January JEE mains. And it has been working for years now. As in when it started, it was the best thing for the Bangalore kids, because what happens from January onwards, these quota guys and other Hyderabad quota, they don't care about the board exam. They devote more and more time to JEE mains only. But you guys will be busy with school submissions, reports, board exam, pre-boards. So they will naturally get ahead of you. Relatively, I'm talking about. So when you attempt in the second attempt, when you do January, when you attempt it in April, you'll see your ranks. Typically, I've seen, I'm not saying for all the cases, typically 95% of the cases, the ranks go down. Okay. It doesn't matter how much hard work you are assuming that you'll be doing, because of the lesser time available to you, others will naturally get ahead of you. Those who are only focusing on JEE mains after January.
So if you write 2 attempts, do they take the best of your rank or the recent best?
Best. But why to take
Take
this?
the risk.
I mean, thing is that if you don't do well in January JEE mains, then you are performing under pressure then. Okay. And under pressure, things going wrong, the chances of that is more. So why not do well in January itself and just get over with it? Your mains is done then. Like your seat in some regional engineering college or the NITs, somewhere what is your worst case after January. That is like best thing to have. So don't assume you have two chances. Give everything you have in January JEE mains itself. All right, so we have around 50 minutes now. We will continue solving problems. I have a lot of questions with me and probably slightly difficult ones. So let us take one by one, all of it. We'll start with the simpler one. Do this.
So
solve the question first, then we'll discuss. Done? I think this is simpler than whatever we have done till now. All right. So fringe width, how to get that? Lambda d by small d. There is a fringe width. You just substitute the values, you'll get the answer. Second one, how to do it? How to do the second one? I don't care about the final answer. Tell me how to go about it. Adjacent minima should be coming to the center. So what should happen?
In the first one, shouldn't we be dividing it by mu? Because lambda given is an air.
Yeah, I was thinking that.
Yeah. Sorry. This is wavelength 6. It is Young's double slit is inside it. So mu into d. Correct. Lambda is different because the wavelength, where it is written, it is in air. Whose
wavelength in air.
Wavelength in air is.
Where it is written wavelength in air?
So next to the 6300.
Wavelength in air, it is written. So apparatus is inside 1.33. Correct. To do that. Sorry about it. So now, if the first dark fringe comes here, you have to find out the smallest thickness of this. How to go about that?
So we can get that T into mu will give us the part difference, and part difference should change by one fringe width.
By fringe width. Here,
yes, sir.
Here what should be there? First minima should be here or not?
Yes, sir.
At the center. So what should be the path difference over here? First minima, what is the path difference? Don't know. First minima happens when the path difference is lambda by 2. Second minima happens when the path difference is 3 lambda by 2. Like this, it keeps on going. Got it? Clear, Ruchir?
Yes, sir. Sorry, sir.
So, can I say that refractive index of the glass minus 1 into T, when this is equal to lambda by 2, I can find out the T. Is this correct or there's something wrong?
So shouldn't it be minus the refractive index of the apparatus? The thing it's immersed in?
Should be 1. It should be 4 by 3. 1.33.
Okay, so not minus of that. It will be this divided by refractive index of the liquid. Getting it? This one.
Yes, sir.
And anything else? Or that's it? Anything else? My wavelength is also changed, na? This. Are you able to understand?
Yes,
no?
sir.
Somehow I'm getting the feel that you guys are unprepared completely. I'm not getting the confidence. Are you able to understand this? All of you? Type in yes or no. What is the doubt? Speak a bit, na? Don't be like this.
So the ratio part I didn't understand of the
ratio chod. Did you understand what I've done right now?
Yes, sir, that I understand.
That is what I'm asking. All of you understood this?
Yes, sir.
Okay, so lambda divided by 2 times mu g minus mu L. Who is asking ratio where it is?
No, sir, the mu g by mu L I was asking.
Oh, that. Okay. See, you have to take relative refractive index. Suppose you have a glass, okay? Suppose the refractive index of glass sheet is same as 1.33. Will it make any difference? The refractive index of glass is same as what is here. It's like this apparatus is in air, let's say. This glass is also made up of air. Will it make any difference?
No, sir.
Suppose this refractive index of liquid is 4 by 3 and the glass refractive index is also 4 by 3. This glass won't do anything. It will not deviate the light. It will deviate light only when the refractive index of the glass is different from the medium. So you need to consider relative refractive index. Relative refractive index you need to consider when you are finding the path difference mu minus 1 into t. Mu is relative to the medium, okay? Right now, if it is mu, you're basically writing it as mu divided by 1, where 1 is refractive index of air, which is right now the medium. Clear?
Yes, I understood.
Sir, even for that lambda by 2 mu L, so in the previous question, even for that lambda by 2 mu L also, you have taken relative refractive index.
See, relative refractive index is taken when refraction is happening at the interface of two mediums. The interference is happening over here where only 4 by 3 is there, right? Here. When you consider what happens because of glass, then you consider relative refractive index. Wavelength will change. Over here, you need to consider as lambda by mu. Okay, there should not be any doubt on that. There is no glass over here where interference is happening. Clear?
Yes, sir.
Okay. Do this. Don't get scared by the size of the question. Let's do one by one. Part A you have to do first. We'll discuss it and then part 2 and part. Done with part A. While you're doing part A, don't forget to read this thing, which is there in bracket. Okay, this thing is important. Wavelengths are given in 4 by 3 the medium of 4 by 3. It should not divide wavelength by 4 by 3. Okay. Fringe, the central bright will shift upward or downward? What do you think? Everyone, upward or downward?
So I think downward.
You think downwards.
So because it bends towards the normal, so downwards.
No, that is not the reason. What is the definition of central bright?
Path difference is zero.
Path difference is 0.
Path difference is 0. So the lower light is traveling extra path because it is traveling inside the glass also. So the upper light has to compensate for it by traveling extra actual distance. Fine. So if this distance is y, the actual path difference should be equal to y by d into small d, right? This should be the path. This is the extra distance traveled by the upper wave, and because of the glass, it is mu minus 1 into t. This should be the path difference or not at any point in time. All of you agree?
Yes, sir.
Okay. Now tell me, there is no ambiguity in y, d, and d. What should be mu? Mu should be what?
Mu 1 and mu 2. Like
1.5 divided by 4 by 3.
4 by 3. Yeah.
This you have to take. Fine. So when you equate that to 0, you'll get the value of y. So y will be equal to what? Mu minus 1 into t into d divided by small d. So this is the value you'll get for part A. So you need to be taking care of many things. I mean, this is where many falter. They don't take relative refractive index. Entire experiment is inside the liquid. I don't know why they are doing that, but don't make silly errors. B part. Now try the B part. You can just write down expression like this. You don't need to get the value as of now, because right now we have to look at other questions also. Done with B. Ajay, tell me at point O, what is the path difference? How much it is?
So
Mu minus 1 t.
Mu minus 1 into t. Okay. Mu you should take a relative 1.5 divided by 4 by 3. Okay. So because of which the phase difference is what? 2 pi by lambda into delta x, which is this. Okay. And intensity formula is what? 4 I naught cos square phi by 2. So delta phi by 2. Okay. Now they're asking you to relative to the maximum fringe intensity. So 4 I naught is maximum fringe intensity. So rather than writing 4 I naught, you just write down I max. I is equal to I max into cos square delta phi by 2. Okay. Now solve the C part. as in tell how to get the C part.
So 5 by 2 will be equal to n pi.
B part you're saying?
No, sir, C part for maximum.
Okay. So at point O, the path difference is mu minus 1 into t. Okay. It will have a consecutive difference if this is equal to n times lambda. So lambda should be equal to mu minus 1 into t divided by integer n. Okay. So you just keep on changing values of n, put n equal to 1, 2, 3, like that. You will soon see that for n equal to 2, let's say your wavelength is more than 400, and n equal to 6, your wavelength is more than 700. So between 2 and 6, you have to substitute n and get the values of wavelength for those values of n. Okay, so like this, you can get the different values of lambda for which this equation is satisfied for the constructive interference or maxima. So what is the learning here? First learning is reading whatever is there at the bracket at the end, because I'm sure many will forget that and they will start assuming that this wavelength is given in air. Second learning is, this we have learned in the previous question also. The refractive index of glass slab is relative refractive index. When you just write it as 1.5, you're assuming it is kept in the medium of refractive index 1, 1.5 by 1. When it is kept in some other medium, you have to divide by that refractive index. Okay. All right. So let's go to the next question now. This one. Somebody joined just now. Who is it? Param. No, Param. Param, it is not getting recorded. Sorry. All of you do this question. Are you done? All of you are done? All right, I'll solve this question now. Focus here. Or should I wait? All right, so this formula of intensity, I1 plus I2
20 seconds.
plus 2 under root I1 I2 cos of phi. This formula assumes, correct, this formula assumes that the opening of both the slits are same. Okay, if opening of both the slits are different, the formula get changed to this P1 plus P2 plus 2 under root P1 P2 cos of phi. Okay, this formula should be utilized for power, but if areas are same, then same formula holds good for the intensity as well. Fine. So power, how to get? P1 is equal to intensity, that is 10 by pi into pi R1 square. P2 is 10 by pi into pi R2 square. Okay, and then this much thickness, refractive index this. Okay, so the path difference delta x is mu minus 1 into t. So the phase difference, let's call it as phi only. Phase difference is 2 pi by lambda times mu minus 1 into thickness t. Everything is given in the question. Okay, so P1 and P2 you found out the phi, and then you just need to substitute over here and you'll get the answer. No, but then here 10% of power is received by each aperture, goes to the original direction. So you can, I mean, this is P1 dash, P2 dash. So P1 which you should substitute is 10% of it. So that is 0.1 times P1 dash. P2 is 0.1 times P2 dash. I hope all of you have understood. This is an important question to make you realize that if the areas or the opening of the slits, they are different, then the equation is valid for the power, not for the intensity. Is it clear to everyone? Any doubt? Any doubt on this? Anyone?
So why was the focus given here, sir? Is there no
Please
relation
type
here?
in yes or no. Any doubt?
So why was the focus given here? Was there any relation or just not?
Copy it down. Let me know if there is any doubt quickly.
So, but while deriving this relation of intensity, we never assume that they have the same area. So, like,
Ruchir, you understood? Parik? Oh, sorry, my speaker was on mute. Say it now. Clear, Ruchir?
So I had a doubt, sir.
Say it.
So this focus, so why was the focus of the lens given the question? Yeah, I'm just trying
Oh,
to
you
relate it.
okay. See, this lens has no role in creating path difference. Okay, because it's symmetrically placed. Whatever happens here, same thing happens there also. What this lens does is that it brings the interference closer to the slits. Otherwise, your screen should be far away. Lens is there so that entire light get focused on the at a distance of f. Okay, that is what it does. Many times you'll see prisms, then lenses, and many other things in the Young's double slit experiment or single slit experiment. So don't uh, get confused if they use that. Most of the time it will be this only. Okay, they are just using it to make sure that you don't have to put the screen very far away location. Clear?
Yes, I could say.
Okay, let us, sir, I thought that since they have different wavelengths, we have to consider different refractive index for both the rays. So both rays have different refractive index.
So like the way that when we did dispersion of white light into all of the different colors, so I thought that like since these two have different wavelengths, you have to consider that effect.
Where are the two different wavelengths?
So
Oh,
one of them is
I
passing
think I
through.
read it wrong. I thought that there was 6,000 and 2,000.
2000 Armstrong is the thickness of the.
Yeah, sorry.
Armstrong doesn't always mean that it is wavelength. It could be Neil Armstrong also. All right. Do this. If you are able to solve this question your own, you are done with the Young's double slit experiment for next 1 year. Okay, who joined just now? Anybody joined just now?
So I left and I joined. My internet was like lagging.
But then it shows 27 people. Anyway, someone left. Do this, guys, on your own. I'm telling you, if you get this your own, you're done. You don't have to practice Young's double slit experiment. At least do the 75% of it. Whatever you do it systematically. Draw the diagram properly. What the amount of time you spend in this question, totally worth it. It will save a lot of time later on. If you want, you can keep it in terms of variable. Take mu1, t1, mu2, t2 like that, and lambda in terms of that. Also, if you want, you can write your values. Thickness is same for both the glass. Anyone closer to the answer, or should I start solving?
So
So
just
could you give 2 more minutes?
Okay. All right. If you get the correct answer your own, that's impressive. All right, Ruchir is done. I got something, just need to substitute values. Ruchir Singh is all, both the Ruchirs. Something in the name Ruchir. All right, so we will now discuss it out, right? Focus here. Param, you're done?
yes, sir. I just have to put the values in.
Take it. Now stop it. All of you also focus here. All right. So let's see how to solve this. It is observed, look at the last line. It is observed that what used to be fifth maximum earlier lies below the point P. So this point P, what is this point P? Where it is the found at P on the screen where central maxima fell before the glass plate was inserted. So central maxima will be at the center here. So the same point P, the fifth maxima is below it. So over here will be fifth maxima, and above it will be the sixth minima. So this point P is between fifth maxima and sixth minima. What does it mean? The path difference for the fifth maxima is how much? Anyone?
So it's for the fifth maxima.
Huh.
So it's gonna be 5 by 2 into.
अबे 5 lambda होगा ना भाई. Lambda is for first maxima, 0 is for center maxima, 2 lambda is for second maxima, 3 lambda is for third, 4 lambda is for fourth, 5 lambda is for fifth. Is it clear?
Yes, sir.
Yes, sir.
Okay, and tell me what is the path difference for the sixth minima? Do it yourself, tell me. Arey,
11 lambda by 2.
11 lambda by 2.
Yes, sir. 11 lambda by 2.
11 lambda by 2. Okay, so I mean, if you are wondering, path difference should be 2n plus 1 lambda by 2 for the minima, right? When you put n equal to 0, that is your first minima, which is lambda by 2. So n equal to 5 should be your sixth minima. That will be 11 lambda by 2. Now tell me what I can say about point P. Anyone? At
Sir,
point, tell me.
so it should lie in this range of path difference.
The path difference should be between 5 lambda and 7 lambda by 2. What about phase difference? Multiply 2 pi by lambda, right? It should be between 10 pi and 2 pi by lambda. It should be 11 pi. So the phase difference at that point should be between 10 pi and 11 pi. All of you understood till now? Any doubt? Anyone has any doubt? No doubts. Okay. Fine. So now let's proceed further. It has 3/4 the original intensity. We are going to use this information now. Whatever was the original intensity before the glass plate was put. Now, before the glass plate was put, the intensity over there was 4 times individual intensity, 4 I naught. Now the intensity has 3/4 of that. Fine. So intensity is 3/4 of the original intensity at that point. That will be 3 I naught. Okay. And this should be equal to 4 I naught cos square 5 by 2. Right? I is equal to 4 I naught cos square 5 by 2 and I is 3 I naught. So cos of 5 by 2 will become equal to root 3 by 2. Okay. From here, plus minus. From here, 5 by 2 is equal to n pi plus minus pi by 6. Or phi is equal to 2n pi plus minus pi by 3. Now tell me what is the value of phi. Use the first equation, this one, and the second one. Tell me the value of phi, how much it should be.
So 10 pi plus pi by 3.
That is how much?
31 pi by 3.
31 pi by 3, right? So phi equal to 31 pi by 3. This phi satisfies it. Every other phi doesn't satisfy the first equation. So phi should be this. So we have got the phase difference at that point. Clear, right? Any doubts till now? Please ask doubts. Rajdeep, doubt? Arey, Rajdeep nahi hai. Where is Rajdeep? Okay, Mehul, any doubt? Anyone else? Param, is it clear?
No, sir.
It is not clear.
Not the whole thing divided by 2 because I took 5 by 2 lambda.
अरे doubt मैं बोल रहा हूँ. Whatever I have written, you have any doubt?
It's all clear.
What?
It's all clear. It's all fine.
Okay, Mehul, you were saying something?
Nothing, sir.
Okay, fine. So we have got the phase difference phi, and now we know the path difference is what? Path difference will be mu1 minus 1 into t minus mu2 minus 1 into t. Is there any doubt that this is the path difference? Path difference due to the upper glass minus path difference due to the lower glass will be this much. Okay. So the path difference delta x will be equal to mu1 minus mu2 into t. You got exactly this. Okay, smart. So this is the path difference, and corresponding to it, the phase difference is 2 pi by lambda times path difference, mu1 minus mu2 into t. Okay, this is the phase difference, and this you should equate to 31 pi by 3. Fine. So from there you get the value of t. All right. I hope this question is clear. You'll get t from this equation. Okay. What we have learned in this equation, something very important. The value of phi is not unique for cos of phi by 2 to be any angle. So we tend to forget that. We know it, that it is true, but we tend to forget it. We take the minimum value of phi all the time, but that doesn't work. Any doubts on the entire solution? This is the only question in Young's double slit experiment which I liked, and I keep on doing this question only whenever I teach Young's double slit. No doubts, right? Okay, so we have around 8 minutes. We can probably solve some simpler questions. Whatever I have, we'll finish off. We'll quickly finish off whatever I have left over. Tell me, this one. All right, the answer is D. D for Delhi, because the wavelength has become so less and frequency has become so high that the wave nature is almost completely suppressed. X-ray will behave like a ray. Even the name says it is a ray. All right. This one.
So what do we have to find here, sir?
What do you find?
So do we have to
Yeah. I'm sorry. There was one another part of the question. I missed it. Here it is. Now it makes sense. In order to solve this question, assume D is very less compared to capital D and try using the basics of Young's double slit experiment. Okay, try using Young's double slit experiment principles here. You'll get a lot of such questions. All right, so let us discuss. Let's discuss this. So here in this diagram, you need to assume it like a Young's double slit experiment. How can we assume it? Let's take it over here. Okay, I'll make some space. So if you assume that it is a part of Young's double slit experiment wherein the light is coming from here, okay, this is slit S1 and this you can treat as if it is slit S2, okay, and then if you find out the path difference between the two waves, this wave, okay, sorry, this is, I mean the diagram itself is not to the scale. So assume this is a straight line. Okay, it will be weird. So just give me a moment, I'll correct it. We'll correct it. I keep it like this only. So what happens is, let's say this is S1 and this is P and this is Q. The path difference is actually equal to S1P plus PQ
minus SQ plus minus lambda.
Rahul, mute yourself. S1P plus PQ minus S1Q, right? This is what it is. Now, if I assume it is part of Young's double slit experiment, then I can say that, S1P, if I just extend this line, if I just extend this line, right now it is not to the scale, and extend this line vertically down, okay, you'll get two congruent triangles here, wherein S1P will be equal to S2P. Fine. So you can say that this part difference will be S2P plus PQ minus, see, there will be part difference because of reflection also. I think Rahul was saying that, but that I'm not considering as of now. So hold on. So this will be the part difference, and S2P plus PQ is S2Q. So S2Q minus S1Q, as if it is Young's double slit experiment, and the value of D over here is 2D because the triangles are congruent. This is also D. Fine. So once you draw the analogy with the Young's double slit experiment, you can find out at what distance. I'm doing the B part first. What distance does the first maxima happen? So we know that y is equal to n lambda d by d is the formula. Instead of d, you have to write 2d over here because d is actually 2d from here to here, distance between the two hypothetical slit. The second one is hypothetical. So the first maxima will happen at a distance of lambda d by, okay, hold on, sorry. There's a reflection, I completely forgot about it. So this is the path difference, right? And the path difference is y d by d, where the value of d you have to write it as 2d. Okay, this is 2d. Okay, this, and because of the reflection, you have to add lambda by 2. Once this becomes equal to lambda, first maxima will be observed. Any doubts to anyone? Whatever we have done?
So where did we equate it? Okay, n lambda. Got it.
Always remember that consecutive interference, the path difference should be n lambda. When n is equal to 1, first maxima, like that. Okay. So y will quickly finish off. Hold on, guys. It's already 8. Lambda by 2. So from here, y is equal to lambda d by 4d. Okay, at this location, you will get the first maxima. Fine. As you know, the second slit is hypothetical. Geometrically, it is as good as Young's double slit experiment. That is the most important learning from this question. And A part, let's quickly solve the A part. What will be the intensity at a point just above the mirror, above O, over here? Tell me what is the answer?
That's 0.
Why?
Because so like the path difference is 0 and we added a lambda by 2. So
correct.
That's
So you need 2 waves for interference. One wave will directly go to O, other wave will go like this, reflects off just before O and meets the second light that is reaching O. So one light is getting reflected, other one is directly reaching there. Because of reflection, lambda by 2 will be introduced, and whenever these two light meet, they will have a path difference of lambda by 2 and the intensity will become 0. There will be destructive interference happening there. Destructive interference. Now here we are assuming that same number of light, same amount of light directly reaching O and same amount of light is reflecting off and reaching O immediately, I mean just before O. And that is a reasonable assumption because the point O can be treated like a point which belongs to both sides, the mirror as well as air. So half of it belongs to air, half of it belongs to the mirror. So the light belongs to half of air and half of it comes from the reflection. So that point will be dark. It will have a destructive interference over here. All right. So I hope all of you now appreciate the wave nature of light. We have learned everything in great detail, and you guys are now equipped to solve any question at any level on wave optics as well. Fine. So that's it from my side. In wave optics, next class we will start current electricity. All right. Bye for now. Good night and take care.
Thank you, sir.
Thank you, sir.
Thank you, sir.